Welcome back, folks. We're going to analyze our first circuit with an op amp, and we're going to do it with nodal analysis. This is a common op amp circuit. A lot of people can look at this circuit and immediately tell you what the gain is, and if you know the gain, you can find the output. Let's do that. If you've seen op amp circuits in your other classes before, there it is. But let's apply nodal to it, because that's really what I want you to be able to do, is take any op amp circuit and use nodal analysis. Mesh is a little ugly with op amps. I stay away from mesh analysis when I see an op amp. I usually go right to nodal. And it scales nicely. I've done analysis on op amp circuits that have 9, 10, 11 op amps in them. And if you write the equations correctly, you can have a good calculator, MATLAB, do all the analysis for you. I guess not all of the analysis. You can have it do all the algebra, which is awesome. Okay, so most people would look at this circuit and say, okay, the gain of this circuit, since it is what we call an inverting, this is an inverting op amp circuit. Okay, so we can find a book. You can probably find it online pretty easily and say, okay, this is an inverting op amp circuit. What's the gain? And we would say, well, it's 15K over 3K. Okay, so we would define our voltage gain as negative 15K. The negative is the inverting part over 3K. Okay, so that looks like it's going to be negative 5. And that unit on that is going to be volts per volt. This is how you would typically do it, right? You just have to look at the circuit, know what it is, and get there. Okay, so then we can say that V out is equal to 10 volts times, let's stick some parentheses here, negative 5 volts per volt. Okay, and that's negative 50 volts, right? Because look at our units, those drop out. And we're left with volts, negative 50 volts. Okay, that's great. It was fast, right? But this is for a circuit that's well known. What happens when you have a circuit that's not well known? So what I want to do is take this very well known circuit and get to the same solution, but get there using nodal analysis, because nodal analysis is going to be more versatile. Okay, so how are we going to do that? We're doing nodal analysis, so there's only a couple little wrinkles. A lot of things stay the same. So we label our non-reference nodes, and we look for passive components, and we label the current directions arbitrarily. Just pick. The op amp can add energy to the circuit. There's an additional voltage supply that it's plugged into, and it can add energy. So therefore, the op amp is not a passive circuit element. So let's start off by saying, here's a non-reference node. Hopefully you were looking at it and trying to figure it out for yourself. Here's a non-reference node. Okay, that one lines up all the way to there. Some people are going to be tempted to throw one there, but whoa, be careful, because I can get all the way to ground without crossing a component. So that is ground right there. Okay, and then we have one over here. That's a non-reference node on the output. Passive component, and then passive component. All right, so that's good. Now we have to make our plan, and we have to use the assumptions about the op amp that I talked about in the previous video to help us build that plan. The voltage here is going to be equal to the voltage here. Okay, that's useful. And there's no current going in or out of these input terminals. We can't say the same thing over here. All right, so when I make my plan, I usually start off with nodal analysis. I say how many voltage supplies, and well, we have one. Now we're going to say how many op amps as well. Okay, so how many voltage supplies and op amps. And I count one voltage supply and one op amp, and that's going to force me to write 2 KVLs. Okay, and let's just say one for the 10 volt supply, and one for the op amp. All right, now I make up the difference. I still have 3 unknowns, so I do need 3 equations, and it's 1 KCL to make up the difference. Doing that covers my 3 unknowns with 3 equations. All right. Again, usually where I ask you which one, I got to get my dice out. I think they're still in my office on campus. Tough luck. I ask you which one we want to work with. Okay, so let's get the KVL for the 10 volt supply out of the way. So I would call this the KVL for node A, since that's the only node that we're interested in, and we say, okay, on the positive side of the 10 supply is VA, on the negative side of the voltage supply is ground, and that's equal to 10. All right, that obviously drops out, and VA is simply equal to 10. Okay, that's the nice and easy one. Let's write the next KVL, and the next KVL is going to come from our assumption that these two voltages are the same. Okay, so that assumption might look like this. It's 0 volts. I didn't really think about the polarity there because it's 0 volts. All right, so from there to there is 0 volts. And then VB exists from B to ground, right? So we write our KVL around this little loop here. We start here, we go up, we come back down. It's a KVL. It's just a very simple one. Okay, I can squeeze that in down here. KVL for the op amp. All right, we're going to go up VB. We're going to go down 0, and we're back to where we started, so that's equal to 0. So we find that VB is equal to 0. And that's our equation. Okay. Let's see, I typically write this by looking at one of the terminals, and I start with the positive one. It's 0. Okay. And I write it a little faster, but I get to the same place because it's not always going to be connected to ground. Okay, so I take whatever node is attached to the positive. In this case, it's ground. I subtract whatever node is attached to the negative, and then those have to be 0, right? Because if they are in fact the same value and I subtract one from the other, I should get 0. So that's another way that I write this. And then if that cancels out and we multiply left and right by -1, we get back to the same place. Okay, so you'll see me do that, and I'll talk my way through that as I'm writing these in the subsequent videos. Okay, so hey, we're 2/3 of the way there, and we've barely done any work. Fantastic. We've got to write the one KCL, and we've got to write the KCL for a node that we can write all of the currents for. So there's some things that I avoid. If I look at A, I can't write the current through the voltage supply. We've already seen that one. We've run into it before. So I'm not going to write a KCL when I'm trying to find the node voltages for a node that has a voltage supply connected to it. Okay, so let's get some notes down here. So for the KCL, is this behind me yet? Nope. Avoid. First thing I'm going to avoid is nodes with a voltage supply connected to it. Let me get that up over my head here. And I'm not saying independent, dependent, I'm saying voltage supply. Okay, avoid that. So that's going to force us to avoid A. The other thing I'm going to avoid, let me get back to my schematic, is the output of the op amp. And I'm going to avoid the output of the op amp for the same reason, because there is some current here and we don't know what it is. So if I write the equation, the KCL equation for node C, I'm going to introduce an unknown, and then I have to just write another equation anyway. So I'm not going to do that. I'm going to avoid the output of an op amp. Okay, so let's see. So it's important that you know the difference between the outputs and the inputs. We can assume something about the inputs. We can't about the output. And that's why we avoid it. Okay, so if I can't write it for A and I can't write it for C, then that leaves me with B. And I can write the KCL equation for B because of the other assumption about op amps. This current, I'm going to try to squeeze it in here, that current is assumed to be 0 amps. And because we make that assumption, we can write this current, and we're good to go. Okay, so let's do that. VA minus VB over 3K. That's going into node B. Okay, I'm going to have to do a little scrolling. I do apologize. This is the KCL for B. So VA minus VB over 3K. Okay. I'm going to write it this time, but it's a 0, so I'm really going to start dropping it out and ignoring it after a while. This is the current for the input terminal of the op amp, and it's 0. So it doesn't affect the equation. Okay. This current is leaving VB minus VC over 15K. Okay, so we get this one minus VB minus VC over 15K. And that's everything connected to the B node. So it's going to be equal to 0. That looks like our equations that we've had before, right? The 0 drops out, and now we just do the same bit of algebra that we've been doing. So 1 over 3K. Let's see. I'm going to let the calculator chew on this. I'm going to put a plus, and we're going to have negative 1 over 3K, negative 1 over 15K in front of VB, and plus 1 over 15K in front of VC, and that's equal to 0. Okay. Let's see here. Oh, we should get them in matrix form. This is our third equation. Took a corner off that 0. We'll just have to live with it. Our other two equations look like this. They're nice and simple, about as simple as they can get. Squeak that one over there. Squeak that one over right below it. And those are 3 equations. Look at them all. They're all a bunch of constants and our unknown node voltages. We're good to go to solve it with a linear system of equations. Okay, so 1 over 3K. And like I said, I'm just going to let the calculator chew on that. I don't feel like reducing that in my head, although I don't think it's horrible. But I know better. Okay, and we're going to invert that and multiply it by the right hand side. So for this one it's 0. Okay, and this of course is going to give us our vector of unknowns, VA, VB, VC. Okay, after we fill out the rest of it. The next 2 lines are a lot easier to enter in the calculator, that's for sure. Let's see, VA, so the coefficient of VA is 1. The coefficient of VB for that top equation on the right is 0. And the coefficient for VC is also 0. Right hand side is 10. All right, doing the same thing for this lower right corner equation. The coefficient of VA is 0. The coefficient of VB is 1. And the coefficient of VC is 0. And the right hand side is 0. Okay. Plug it in. I got Old Faithful here. So we're going to do 3K inverted, negative 3K inverted minus 15K inverted, 15K inverted. 1, oops, forgot the right hand side, 0, 1, 0, 0, 10, 0, 1, 0, 0. And out of that, we get, well, 10 volts. Oh, shoot, I could have done this in my head. We get 10 volts. Well, it better be, right? We have an equation explicitly stating that. And 0 volts, same comment. We have an equation explicitly stating that. But out of VC, we do find that we have negative 50 volts. Okay, So it was much, much longer to do it this way. Oh, we got to look at what our output was. What was our output? V out. Okay, so our goal here was to find V out. Okay, so C is on the positive side, ground is on the negative side. So that's going to tell us that V out is equal to VC minus 0, which is equal to negative 50 volts. Okay. Took a lot longer than being able to look at the circuit, having a formula, applying it. But what I hope you're starting to see is that we can do nodal analysis. We have these little assumptions that we got to work with, but it's going to work out. Okay? Follow the process, know the assumptions about the ideal op-amp, and you can get to the right answer for any op-amp circuit. And I think that's where the true power lies in performing nodal analysis. Okay? So we're going to need to practice this. We're going to look at one more common op-amp circuit, and then I'm going to mix it up a little bit with some op-amp circuits that I've pulled from various places that you're not going to have the formula for, and that's the fun part. Okay? That's the power. Stay tuned and good luck.